As we go through the different presentations here, I asked if anybody wants a hard copy of the agenda or if you have it electronically, but in here, as you'll see, there's something that there's a presentation, a page number. So in your electronic ones, they might have on your laptop. If you want to follow along, this one starts on page 17. And so all of them will have a similar number on that, with the exception of, it looks like reinforcement number 7, the page is 12 a.m. So a little typo by the instructor on that. Okay, so let's look at structures. So before we start going into here, who would give me a definition of a structure? Just to throw anything out. There's all kinds of things that are right. What's a structure?
Load-bearing component that's based on foundation?
Load-bearing component based on foundation. We can probably write that up here and for every class. That's good. So it's bearing a load. It means it's carrying something. It's carrying a load. Another word for load might be weight. So we're looking at weight. We're building something that's going to carry weight from here to that, oftentimes over nothing or soft. There's bridges that are actually built on, we call them land bridges. They're essentially built over a swamp. Instead of digging out 50 feet of muck, build a low-level bridge right on top of the swamp. So structures can be many different things. We're obviously going to concentrate on vehicular bridges here in this class, but structures also are things like carrying pipes, maybe a water main over a highway, or different things like that. Structures also are containing maybe tanks containing water. That's all structures. Structures are buildings. People live in them. You know, so structures have many different definitions. So. Get this fixed, because there should be no way this thing goes to sleep in a 2-minute break. Just got to push enough buttons again. There's a lot of videos that are available, maybe not a lot, but several videos available on the Bridge Office website. We are going to show the next presentation after another morning break. We're going to show one on the 35W collapse and rebuild. We're also going to show videos on bridge deck construction. We're going to have some videos that Andy will share on bridge piling. A lot of times videos can help us learn, and so we're going to have a couple different ones. In a 2-week time period, we're trying to make it so that there's a couple different learning things that you as students can go. Some people are okay with learning the way we're doing right now. Other people learn better by watching a video. Other people would be better doing dialogue. And so we're going to have some of each. We're going to have, look in the bridge plan. You know, where do you find, what's the information you have? So our agenda for this chapter 1 is looking at bridge types, elements, and spans. We're looking at some contract definitions of things like who's an engineer, who's an inspector, what do different things mean, what are the roles of each. We're going to look at some of the basics of bridge design, and we're going to look at design and construction loads. And this lowest one here, design and construction loads, when we design a bridge, we're designing it that it'll carry the vehicle, the semi, the loaded semi, the wind, the braking forces, whatever that are on that bridge. But also, as you're building, you have to consider that. So like the St. Croix Bridge, for instance, it was built in cantilever construction. That meaning we started from a pier or a pylon, and we went out a segment at a time. until eventually we were sitting out there 300 feet balancing. 600-foot span, 300 from each pier. That was actually the highest loads that that bridge will ever experience. Because once you tie it together, it becomes continuous and the load path changes. And so I also want you guys to be thinking about what is the load during construction? And is there anything that, as we're building forms and false work, what kind of things do we need to be concerned about? So the type of structure and span arrangement depends on many different things: geometrics, site, aesthetics, depth available, and cost. Geometrics, if we're talking about geometrics, what kind of a geometric feature might make a difference in the type of bridge? So one way is straight or narrow. What's another geometric? A curve. Pre-stressed concrete girders can't be curved. They're straight lines. Steel girders can be curved. And so if you have a pretty tight curve, you're going to have a steel bridge. Now, if it's a gentle curve, and we've perhaps seen a lot of them, you vary that deck overhang a little bit. So maybe at the pier it's 3 feet, and out at the center of the span it's 1 feet. It can accommodate some curve. But if you have a real tight radius, you're not going to accommodate it. So you need to go to steel. So that's one thing for geometrics. Site conditions. You're over land, you're over water, you're over railroad. Maybe there's some access concerns. Maybe you got to then make a longer span. And so that can depend on the site condition. Aesthetics. St. Croix, to use that as an example, was a thing where the concrete box girders are even different than a lot of them. And everything is rounded corners. You couldn't do that with a steel member so easily. And so, that all comes in. Depth available. If you have a highway over highway, but you only have 20 feet to play with, you need 16'4" of vertical clearance. That means you only have, say, 3'8". Well, you're going to have probably a little skinny steel beam maybe instead of a deeper concrete beam. And so depth available matters, and obviously cost always matters. So those are all things that make a difference. So different types of bridges. So up on the top is a truss. We don't build too many truss bridges new anymore, but you may be involved in some rehabs of truss bridges. Arch bridge. This is one where the load path will go down through these vertical span roll columns down to the arch, and then it'll push a lateral force out at the bottom of the piers, so like right here. So it's all coming down, the forces are trying to push outward like that. So different forces that come on. Beam bridges, this is what we're probably most familiar with, is you build some piers or abutments and then you go across with a beam. Tied arch, so Hastings, those of you who have ever been down in Hastings, the new Highway 61 bridge, it's this method. A suspension bridge is one where there's some taller towers, and then there are cables supporting it with some hangers. Cantilever bridge, this is an old picture, a diagram of the fourth bridge in Scotland. Cable stay, this comes up a little bit higher, the towers come higher, the cables come down. Right now, preliminary engineering for the new Blatnick replacement is looking at a cable stay bridge and a tied arch bridge for the main channel. So there are a lot of different examples here of type of bridges that we have. So pictorially, here is a picture of a girder or a beam bridge. So the girders are going along here from pier to pier. So in this case, it's a concrete girder. And also, I'll just mention this terminology, girder or beam. Is there a difference? They're pretty interchangeable. If it's a system that has girders with floor beams tying in, then it's a little different terminology. The girders are the main elements. But pre-stressed, oftentimes we may hear pre-stressed girders, and the same token, we can hear pre-stressed beams. So it's not any market difference there. Beam bridges are the simplest, most commonly used structure type. They are what we use. As far as material, I don't remember if I have it in this slide. Pre-stressed concrete that looks like this. Right now is roughly 80% of the bridges that MnDOT puts up in a new configuration. That leaves 20% for steel or perhaps a few. A MnDOT system, they really don't build much for timber, but 80% is roughly pre-stressed concrete. So here's another picture, just a simple basic bridge over a stream, a couple of piers, one on either side of the channel, river, and then abutment up on the slope. Little pre-stressed girders or beams that are coming across with a concrete railing and a concrete deck. So again, very, very standard type of bridge that we would see here. Beams are limited by their standard depths and shape. There's a little diagram in the bridge design manual that shows if we have a 50-foot span, what depth of beam would we need, depth being this dimension. If we go to 100 feet, obviously it takes a little bit stronger of a beam, a little deeper, and so there's also a chart that would tell that. These pre-stressed beams can get up close to 100 or 200 feet, around 180, some of the deeper sections. And you can always stack a few beams a little bit closer to each other. We'll look at some of that when we get into the 27-138 bridge. This is a picture of one of the single point interchanges that we have in MnDOT. I think this is the Penn Avenue. Single point interchanges, the ramps come in and everybody is going, kind of crossing at the same place. There's a traffic light, stop the ramps, and then the ramps go. But it's configuration like this, there's no way pre-stressed girders would work. But steel, you can frame steel into another member. So in this case, there's a beam going from a girder going all the way from here, going across, and then all these little curved ones are coming in and framing in. So this is something that steel can accommodate. Or pre-stress, you'd never be able to do that. So there's just a picture of in this case, a welded plate girder. Welded plate girders simply mean that there is a top flange, a bottom flange, and then a web. The web is this vertical piece. They're welded together in a fabrication shop, and then they come out to the site. They also do have the smaller beams, like up to 36 inches, are what they call rolled steel, and they come out of the rolling mill in the final configuration. So you might see both of those. Concrete slab span does not have a separate beam, but this slab gets a little bit thicker. And so typically they would be in the 16, 18, 20, maybe 24 inches thick. The one thing, it's going to require more false work as you're constructing. Whereas a beam bridge, you build the piers, you put a beam across, and then you just have decking. But in this case, for a slab, you'd have to support it all the way across. So we're going to have a full session on forms and false work, and we'll talk about that a little bit more. Truss bridges always have triangular shaped elements. And their elements are always either just tension or just compression. And who can tell me what is a tension member? What is tension? What's it trying to do? Material. Trying to push it together or pull it apart? Tension is trying to pull it apart. Tension is trying to pull it apart. Compression is trying to push it together. We're gonna talk more, I'll just briefly mention it here. Reinforced concrete combines concrete, which is strong in compression, with steel reinforcement bar, which is strong in tension. You put them together in a bending moment, and the reinforcement will take your tensile stresses. Your concrete will take your compression stresses. These kind of bridges are all steel. It could be a concrete deck, but as far as the structural members, they're all steel. They're all in triangular patterns, and they're going to, all of the loads will go such that each member is just in tension or in compression. And so that is how a truss works. So this is a picture of the Baudette bridge. Part of the problems with truss bridges is they have these portals that are down sometimes fairly low to the above the roadway, and they get hit by high loads. So one of my jobs as Metro Region engineer was, seemed like every couple times a year even, go visit the Stillwater Lift Bridge, because high loads would come and damage a portal or one of the verticals or something. So arch bridges transfer vertical loads into partially horizontal loads that push against the abutment. So without getting in too deep into statics, you get a load coming down here, it's a vertical load, but it's going to distribute because of the shape of this nature. Some will go horizontal, some load will stay vertical, and it'll keep working its way down. But eventually, it is trying to push laterally. So those foundations have to be pretty stout to be able to resist those types of loads. So that's an arch bridge. That's the Lake Street Bridge in Minneapolis. Cantilever Bridge, I mentioned St. Croix, we were about 300 feet each way. Likewise, the 35W, that we'll see a video here after break, they actually built this back span first. This is all, there was false work down here, and they built all this. So essentially it's like a big counterweight. And then each one of these segments was placed day after day after day. And it went out until they got out to the middle, and then they'll put it together. But each of these segments had to be tied back with post-tensioning back to what had already been cast. So that's called a cantilever during construction, and it's a cantilever bridge in that way. A cable stay bridge. So the picture for Minnesota is the Greenway Trail over Highway 55. They've recently had some issues with some of the connector brackets and stuff up both, I believe both up here and down here, for sure up at the tower. And so there's been cracking and stuff that they've had to figure out. But other more famous examples would be things like the Sunshine Skyway Bridge in Florida and so forth. So those are all the types of cable stay bridges. Extrados Bridge, I hadn't heard this term really until I started working on the St. Croix project. But this is kind of a combination between a cable stay and just a conventional box girder. But if this was a cable stay bridge, these towers would be much taller. It would be up, these were 65 feet tall. We'd probably be at least 200, maybe more. But we would also then eliminate at least one of these. These were 600-foot spans, so a true cable stay would probably be at least a 1,200-foot span, or could be that much. A Blatnik right now is looking at about a 750-foot span for a cable stay. But an Extrados bridge utilizes post-tensioning. These are post-tensioning strands. There's also a lot of post-tensioning that runs in the box. But essentially it enables you to have less post-tensioning in the box itself. So a combination of stay cable and concrete box girder design. Suspension bridge in Minneapolis, we have the Hennepin Avenue Bridge. And it's a shorter span. It was made as a suspension bridge to replicate what was out there originally back in the late 1800s, early 1900s. And so they can go much longer than that Hennepin Avenue suspension bridge is, but that is. Is this a bridge?
Yes.
Yes. What makes it a bridge?
Road over traffic.
What?
Road over traffic.
It's over 10 feet. So it's holding traffic, it's a little bit, it's over 10 feet. It can also be a bridge if, you know, this one does look like it's more than a 10-foot span, so it's a bridge on its own. Also, if we had, say, a 6-foot box with less than a 3-foot gap between and then another 6-foot box, that would also be a bridge. And so that is the definition that we have. So in Minnesota, culverts that measure over 10 feet horizontally on the center line are considered bridges. Substructure versus superstructure. The superstructure is the part that vehicles drive on, part that gets the loads from one substructure to the other. So the superstructure is the part of any of these big concrete elements. The substructure is the piece that's down here. So we'll see some more terminology, but among the things in the superstructure is the deck. It's also going to be the barrier or the railing. It's also going to be the beams or the girders. And these little guys here are the bearings. They're kind of in no man's land, but we do consider them to be part of the superstructure, and it's part of what is shown here. The substructure then are the parts that carry the loads from the beams down eventually into the ground. So that's going to include, in this type of a diagram, this is the abutment, this is the pier. It's also going to include the footing. So all substructure will have some type of a footing, and a lot of times we'll have some piling that will come down. You can also have, for say a pier, you might not have any footing, you might not have any concrete stem, you might just have a steel pile that come up here, and then some kind of a cap that ties to it. So all of those are substructure elements. So these are some of the major components. I've mentioned them already. Beams and girders. So those are part of the superstructure. Bearings are part of the superstructure. Pier cap is part of the substructure. Pier is part of the substructure. Pile is part of the substructure. So terminology to keep in mind as we go. Pictorially, so the girders here are, in this case, pre-stressed concrete. And they're going to go from pier to pier. We also have then a pier cap, or sometimes it's called a pile cap. So it's this concrete element that's going across. So that is going to then share the load from coming down through the deck, through the beams, through the bearings, and it'll go on. One of the things we always want to look for and think about is what is the load path? And this might be just a good place to point out that if we have a deck up here and we have, say, a semi up in the middle, the deck obviously isn't on here, the loads will come here, it'll come through the deck to the beam. Some of that load is going to say, well, I'm going to come over to this side. Other load will go to that side. The load that comes here is going to come down through here, and that's going to distribute through this concrete member, through the pier cap. Some of the load will come down to this pile, other load will come down to this pile. And so all of that area, all of the stuff that we're building has a purpose to share the load and distribute the load into a certain place. And so load path, load transfer is a big thing in structural engineering, and understanding what it means will really help you out. It's looking at what we call an elevation view. An elevation view is looking at the side of a bridge. And the elevation view here is looking at beams. We're looking at damage of beams. We're looking at a pier cap. Over here, we're looking at piers, the piers that are controlling that load. Crash walls. So a lot more emphasis nowadays placed on crash walls. That if, if a semi were to crash into something, what would happen? So those are all the things that we have. Above this red line, what's it called? Superstructure. Below that red line is substructure. There we have it. So terminology of what's what. The reason this becomes important in our spec book is there's actually different things for curing, there are different requirements for curing concrete if you're a substructure element or a superstructure element. If you're a deck versus a pier. So terminology matters. It's things that we want to keep in mind of what our needs are. So here, looking at a typical bridge, I don't remember, I took this one from 27-138, but at any rate, it's similar. So the pier footing is the pier footing, the box down here. The pier, in this case, would be a column plus whatever kind of a cap. The beam and the girders are these parts that are going across here. The abutment, in this case, a footing up on the fill, and then the abutment over there. A wing wall. It's this portion that goes back from the abutment, and it's going to withhold the dirt fill that's back behind the abutment. So oftentimes these abutments, especially if they go down to this level of the roadway, it's at least 20 feet of fill. And you can imagine if you didn't have a wing wall, how would you hold up that fill? You could hold it right immediately at the abutment, but it would just keep spilling out the sides. And so the wing wall retains that. So sometimes the wing walls go parallel, sometimes you go back at 45, sometimes, depending where you are, maybe you're attaching to a retaining wall along the roadway, so they might come out parallel essentially to the road. Slope paving, we're going to learn about slope paving and how we construct that. So its purpose is to make sure you don't have erosion coming down underneath. So some common types of beams or girders. So steel girders are suitable for longer spans. The steel can get up to 300 feet, especially if you haunch. Box girders, so steel can be put into a box type shape. This case is showing a steel box with a concrete deck on the top. The top one is showing a concrete box. Concrete boxes have a good ability to be able to be formed into curves, into different geometric things, so they become pretty valuable that way. And then plate girders can be more stout, like railroad bridges will often have this kind of a configuration, maybe some heavier diaphragms and stuff going in there. So. More pictures of steel on the left. Oftentimes they will require a shoring tower at a certain location. So as the designer makes a plan, they will say, well, where's my splice locations? And you have to support my girder at such and such a location, at elevation, before you put the next one on. If you don't, then you can get some weird geometrics in there. So there's always going to be these little things you see as X's in here. They're called diaphragms. And they will tie all of those pieces together. Any single, if it was just one single girder, it would be very unstable. You'd get a curved situation like that. But you tie all these together with these X braces, and they become much more stable. This is a concrete box girder. This is a cast in place, we can tell by the rebar that's sticking out of the end. And so there's forms that come along, and then they form it up and put rebar and